We now deal with objects that are in free fall. And an object that is in free fall is an object on which gravity is the only force acting. There's no air resistance, there's nobody throwing anything or pushing anything. When something is in free fall, gravity is the only force that's acting. And a difference with regard to free fall in terms of common everyday speech and physics. In common everyday speech, when something is described as being in free fall, it is assumed by the listener to be traveling downward. And that is not always the case in physics. In physics, free fall means gravity is the only force that's acting, and therefore the object could be traveling upwards. If I throw a ball upwards, it could be traveling downwards, like if I drop a ball from a high elevation, or it could be not moving at an instant when it, say, gets to the top of its path. So that is a very important and significant difference that you must know. In physics, free fall does not necessarily mean the object is falling towards the Earth. It means that gravity is the only force. It could be traveling upwards, it could be traveling downwards, but gravity is the only force that's acting. The nice thing is that when something is in free fall on Earth, we know the value of its acceleration. We never have to be told that it's this value. It actually varies at different locations on the Earth's surface, but that is the value that we're going to use. Unless we're told otherwise, we're going to assume that all of our problems take place on Earth. And if an object is in free fall, its acceleration is going to be that number right there. Now, is it a positive 9.81 or is it negative? It doesn't matter. It's whatever you define. If you define up to be positive, then the acceleration is going to be negative 9.81 meters per second squared. If you define downward to be positive, because you can do that if you want, then the acceleration will have a positive 9.81 meters per second squared. We'll run into this more as time goes on. Here we're going to fire escape an alarm clock from rest, which means that V initial is 0, and the height is 38 meters. So that is some kind of a displacement, isn't it? And we know that the acceleration, it has a magnitude of 9.81 meters per second squared. All right, now, do we want this to be negative or positive 9.81? Most of us think, oh, downward is going to be negative. That acceleration always points towards the Earth, and therefore, if you choose towards the Earth to be negative, then yes, that will be negative. Which also means, doesn't it, that the displacement of this alarm clock is towards the Earth. So therefore, the displacement of the alarm clock is also going to be negative 38 meters. If we had chosen downward to be positive, then the acceleration, which points downward, would be positive, and the displacement of this alarm clock would also be positive. So either, for this case, they're both negative or they're both positive. It doesn't matter which one. How long is the clock in the air? We're looking for the time. There are any number of our equations that we could use. I suggest we use this one. The initial velocity is 0, so that term goes away. If we solve this equation for time, it's going to end up being 2 times d divided by a square rooted. 2 times the displacement is negative 38 meters. The acceleration is negative 9.81 meters per second squared. And then we're going to want to take the square root of that whole thing. And when we do that, we get 2.78. You can see right here where these negative signs, they're both negative, and that is really good because then we can take the square root of that positive number. The other alternative was that the 38 and the 9.81 were both positive. If we had chosen downward to be the positive direction, and in that case too, we would have gotten 2.78 seconds. So that works out just fine. Letter B, find the velocity of the clock at impact. That sounds to me like a V final. And what do we know? We know V initial is 0. We know the acceleration. We've chosen downward to be negative, so we're going to say negative 9.81 meters per second squared. We also know the distance that it travels, the displacement that is. The clock is traveling downward, and once again, we've chosen downward to be negative, so that displacement is going to be negative 38 meters. We could use this time if we wanted, but I think we should, where we can, use only the variables that are given in our problem to help us solve this one. So we're going to use the no time equation. Even though we know the time, and you can use another equation if you want to help you, but if we miscalculated this time and then we use that time in part B here, then we're going to get a wrong answer for that one as well. So how are we going to do this? VI is 0, so VF is going to be the square root of 2 times A times D. And in your math classes, you might have been told whenever you take the square root of both sides, you're supposed to put plus or minus. Let's do that and see if that has any meaning for this problem. 2 times negative 9.8, 1 times negative 38. We're going to end up taking the square root of a positive number, which is good. And the magnitude I get is 27.3 meters per second. Now, should we choose positive or should we choose negative? This clock on the way down is moving in the negative direction. So we need to choose the negative version. If we were asked to find the speed of the clock at impact, we would simply report it as 27.3 meters per second. Another way to write this is you could say 27.3 meters per second downward. That would be an acceptable answer as well. Velocity, we need direction and magnitude. What about part C? Part C says find the velocity of the clock halfway down. So once again, we're looking for a V final. It's not the V final that we got when the clock hit the ground. It's the speed when the clock is only halfway down. Well, halfway down, the displacement isn't going to be 38 anymore. It's going to be 19, negative 19 meters. We still know the acceleration to be negative 9.81 meters per second squared. So I think once again we should use the no time equation. V final squared is equal to V initial squared plus 2 times A times D. V initial is 0, which means V final, as we did before, plus or minus 2 times A times D square rooted. Are we going to choose the positive or the negative form of this? Halfway down, we're going to choose the negative form of this one again, because halfway down, the clock will be moving in the negative direction, which we defined from the beginning. I got 19.3 meters per second. The negative gives us the direction. The other alternative there is to go 19.3 meters per second in that direction. Whenever it says velocity, see where I'm circling? Whenever it says velocity, you have to have the magnitude and a direction. And here, the direction is indicated by the negative sign. Here, the direction is indicated by the arrow.